Hey everyone, welcome back to the channel. Today we're diving into something that's revolutionized our world, the microchip. These tiny marvels power everything from smartphones to cars. Ever wondered how these intricate circuits with billions of transistors are made? It's a fascinating process involving cutting-edge technology. We're talking about structures so small, you need an electron microscope to see them. So buckle up, because we're about to explore semiconductor fabrication. We'll break down each step from design to packaging and give you a peek behind the curtain of this incredible industry. Don't forget to like, share, and subscribe for more tech insights. Before a single silicon atom is touched, it all starts with a team of brilliant engineers and their digital drawing boards. They're the architects of the microchip, planning every transistor, capacitor, and circuit pathway. Imagine mapping out a city with billions of inhabitants, each with a specific job and route. They use specialized software known as electronic design automation tools to create the blueprints for these intricate circuits. These blueprints, called photomasks, are like stencils used to etch the circuit patterns onto the silicon wafer. It's like using a cookie cutter but on a microscopic level with insanely high precision. Engineers also consider factors like power consumption, heat dissipation, and signal integrity. They run countless simulations to optimize performance and efficiency. Once the design is finalized, it's time to move from the digital world to the physical realm. Alright, so we've got our blueprint, our digital map to microchip nirvana. But we need something to build on, right? Enter the silicon wafer. Silicon is one of the most abundant elements on Earth, found in sand, quartz, and other rocks. The journey starts with extracting pure silicon from silica rock. This involves serious heat and chemical reactions, resulting in a chunk of purified silicon known as an ingot. This ingot is then sliced into thin circular wafers, kind of like slicing a loaf of bread, but way more delicate. These wafers are incredibly thin, typically less than a millimeter thick, and incredibly flat. Any imperfection on the wafer surface can mess up the entire microchip manufacturing process. These pristine silicon wafers are then polished to a mirror-like finish, ready for the next stage. We've got our pristine silicon wafers, prepped and polished to perfection. It's time to start building those intricate circuits. That's where photolithography comes in. Imagine you have a flashlight and a piece of photosensitive paper. Shine the light on the paper, and you create an exposed area. Photolithography works similarly, but instead of a flashlight, we're using ultraviolet light. And instead of paper, we have our silicon wafer coated with a special material called photoresist. This photoresist is sensitive to UV light, causing a chemical change that makes it either more or less soluble in a developer solution. The photomask, which contains the circuit pattern, is placed between the UV light source and the silicon wafer. The UV light shines through the transparent areas of the mask, exposing the photoresist beneath. The unexposed areas, protected by the opaque patterns on the mask, remain unchanged. Next, the wafer is bathed in a developer solution, washing away the exposed or unexposed photoresist, leaving behind a pattern that matches the circuit design on the photomask. It's like magic, but instead of spells, we're using light and chemistry to create the building blocks of our microchips. The level of precision here is mind-blowing. We're talking about creating features just a few nanometers in size. We've got our photoresist pattern on the wafer, outlining the intricate circuitry of our future microchip. Now we need to carve those patterns into the silicon itself. That's where etching comes in. It's like using a microscopic chisel to sculpt the silicon landscape. There are two main types of etching, wet etching and dry etching. Wet etching is like using acid to dissolve away the unwanted material. Dry etching, on the other hand, is like using a tiny sandblaster, bombarding the wafer with plasma, a superheated, electrically charged gas. This plasma selectively removes the exposed silicon, leaving behind the protected areas defined by the photoresist pattern. The etching process is like using a tiny jackhammer to carefully chip away at the exposed silicon, creating the desired patterns. The actual process is far more complex, involving precise control over the etching time, gas composition, and temperature. Too much etching, and you risk damaging the wafer. Too little, and the circuits won't be properly defined. It's a delicate dance between precision and power, crucial for creating the intricate three-dimensional structures that make up modern microchips. Modern chips can have dozens of layers, each with its own unique etching challenges. We've etched our silicon wafer, creating a maze of trenches and pathways that will become the circuitry of our microchip. But raw silicon isn't particularly useful for building electronic devices. That's where doping comes in. It's the process of intentionally introducing impurities into the silicon crystal lattice, altering its electrical properties. These impurities, called dopants, are typically atoms from other elements like boron, phosphorus, or arsenic. These extra or missing electrons create holes or free electrons in the silicon crystal. These holes and free electrons allow electricity to flow through the silicon, making it conductive. By carefully controlling the type and concentration of dopants, engineers can fine-tune the electrical properties of different regions on the wafer. Doping can be done in several ways, but one common method is ion implantation. This involves bombarding the wafer with a beam of high-energy ions, which embed themselves into the silicon lattice, effectively doping the material. This process is crucial for creating the different regions needed for the microchip to function. We've etched our silicon wafer and doped specific regions to fine-tune their electrical properties. Now it's time to start building up the chip, layer by layer, like constructing a microscopic skyscraper. This is where deposition comes in. It's the process of adding thin films of various materials onto the wafer, creating the different components of our microchip. These films can be conductors like copper or aluminum, or insulators like silicon dioxide. We're talking about layers that are only a few nanometers thick, deposited with atomic-level accuracy. One common method is chemical vapor deposition, or CVD, where the wafer is exposed to a gas containing the desired material. Another method is physical vapor deposition, or PVD, which involves physically depositing the material onto the wafer. These deposition processes are repeated multiple times with different materials and thicknesses to build up the complex layered structure of a modern microchip. It's like creating a high-tech lasagna, with each layer playing a crucial role in the final product. We've etched our silicon wafer, doped it with impurities, and layered it with various materials. Now it's time to create tiny metal wires that connect the different components of the chip. These wires are incredibly small, often just a few nanometers wide, and need to be incredibly precise. One common method for creating these interconnects is called metallization. In metallization, a thin layer of metal, usually copper or aluminum, is deposited onto the wafer. This metal layer is then patterned and etched, leaving behind a network of tiny wires that connect the different components. These interconnects are like the highways of our Silicon City, carrying electrical signals between components. Without these vital connections, our microchip would be nothing more than a collection of isolated components. We've reached the final stage of our microchip's journey. We've designed, etched, doped, layered, and interconnected our silicon wafer. But before these chips can power our devices, they need to go through rigorous testing and be carefully packaged. Specialized testing equipment checks for defects, measures performance, and ensures the chip meets its specifications. Any chip that fails these tests is rejected, ensuring only the highest quality chips make it to the next stage. Once tested, it's time for packaging. This involves encasing the delicate silicon chip in a protective package that provides electrical connections to the outside world. The packaged chips are then assembled onto printed circuit boards, or PCBs, which contain all the other components needed to create a functional electronic device. These PCBs are then assembled into our smartphones, laptops, cars, and countless other devices that rely on microchips, and there you have it. The incredible journey of a microchip from sand to silicon and beyond. It's a testament to human ingenuity and our relentless pursuit of technological advancement. And that's how micro devices are made. We hope you found this video informative. It's mind-blowing when you think about the complexity and precision involved in creating something so small yet so powerful. These microchips go on to power our smartphones, computers, cars, and countless other devices that shape our modern world. They're the unsung heroes of the digital age, quietly working behind the scenes to make our lives easier, more connected, and more entertaining. So next time you pick up your smartphone or turn on your computer, appreciate the incredible engineering and innovation that went into creating the microchips that make it all possible. Remember to like, share, and subscribe for more tech content. See you next time.